These are the solutions to quiz 3. So if matter is uniform throughout and cannot be separated into other substances by physical processes, but it can be decomposed into other substances by chemical process, then this substance is called what? Okay, so if we cannot separate into other substances by physical processes, that means it's not a mixture. So the first part here is giving us information that helps us figure out that it is not a mixture. Because if it was a mixture, we could separate it into its constituent substances. But if we can break a substance down by chemical means into different types of substances, imagine you have something like NaCl. You can separate that into sodium, and you can separate that into the chlorine, and separate the elements, then you know you have some sort of a compound. So if you have a compound, then you can separate it into one or more of its constituent elements, or simpler compounds of those elements. So we know that we have a compound. So if we had an element, we could not separate that into other chemicals using chemical processes, and we know it's not any sort of mixture. Okay, for number 2, how many significant figures are in the number 0.01005020? Okay, so if I'm tracking sig figs here, the leading zeros don't count, those are just placeholders, and then all the other digits count. So I'd have 1, 2, 3, 4, 5, 6, 7 total digits here in the value. So I'm just looking at these digits here. That final 0 is significant because it's part of the actual value. If it wasn't significant, then it would not have appeared with the value. It just would have said 0.0100502, and that 0 wouldn't have been there. So if this final 0 is after the decimal point and after all the digits in the value, then you know it's significant. So that correct answer here would be 7 digits are significant. Leading zeros are not significant. Now think of it this way. If we were to use scientific notation on this number, writing the full number and all the digits, and then times 10 to the minus 1, 2, so times 10 to the minus 2 seconds, so that this value here would still have 7 sig figs, and then you would clearly see that those leading zeros are just holding the placeholder for that times 10 to the minus 2 quantity. I like to throw units into this problem so that we're thinking of looking at values as some sort of a measurement, that the measurement of time would be limited by whatever device you were using to make that measurement, and it would not read off to an infinite number of preciseness. So it's not like this number here is representing some value with an infinite number of zeros on the end. It really is representing some sort of measured value of time out to 7 total significant figures. So moving on to number 3, complete the indicated arithmetic and give the answer to the correct number of significant figures. Okay, so we have multiplication first here. That's 0.00015 times 54.6. I get 0.0819. Now, 2 sig figs here times 3, multiplication rule says that a value should be rounded to the total number of significant figures as the value in the problem with the least number of sig figs. So we're looking at these values. We're all sort of assuming that this is some representative measurement, not a perfect number. It's 0.0015 with some variability in that last placeholder in the value. Same thing with 54.6, some variability. We're assuming this is some sort of measured quantity, an inexact value. The impreciseness of these values is limiting the preciseness of our calculation. So if we just had the first problem, imagine we don't have the addition here, the answer would be 0.0082. Now, we need to do our next step. We don't necessarily want to round more than one time in this problem. So what I might do is set this number up here and then add my next number, because when we're doing addition and subtraction, it's all about where the placeholders line up relative to the same decimal place. So we have 1.0022 ending in the tenths, hundredths, thousandths, 10,000ths position. We have this value here, 0.00819. It also ends in the 10,000 spot. But we do have that extra 9. We could carry it on. It's actually not going to change the answer to this particular problem if we rounded or didn't round. But sometimes it's nice to round only once in a given problem. If we carry out the arithmetic here, we get 93010.1. So 1.01039. So we're going to round up to 4. So the correct answer here should be E, 1.0104. Okay, so not here because this 9 is not significant. Even if it were, we'd be limited to the 10,000ths place, because when we're adding, we want the value to add in that same placeholder. C, we have 0.0082, 2 sig figs. The 2 sig figs there doesn't matter. We're not rounding the 2 sig figs here because of the addition rule. The addition rule says we end in the placeholder, the decimal place of the value that is of the greater quantity. So we look for the placeholders, like for example, let's say we have 2.5 plus 15. The greater placeholder is the ones position. So this value here would round to 17.5, round that to 18, would be the answer. 2.5 plus 15 to the proper number of significant figures. So you look for the higher quantity placeholder and round your result to that particular quantity. Okay, we'll do a lot of sig fig problems in this class to make sure we're on the same page. Looks like we have another one. Interestingly, a simpler one. I don't know why I didn't switch the order of these, but complete the following math operation, report with proper sig figs. So 9.35 plus 3.4. The main trick here is to not just assume that because this has 2 sig figs, then the result must have 2 sig figs. That's not the addition rule. That's a multiplication rule. The addition rule is 9.35 plus 3.4, line it up, and then round to the placeholder that's higher in value, the tenths place as opposed to the hundredths place. And so that's going to work out to 12.75, and then we'll round that up to 12.8. So 12.8 should be the correct answer. And you can, in a way, kind of prove this rule to you if you're thinking of, let's imagine we're taking 75 plus 75 versus 75 times 75. So if you're ever stuck or you're wondering why is the sig fig rule the way it is, imagine the variability in 75 times 75 if you have like that plus or minus 1. So imagine 75 times 74 or 75 times 76 and see how big of a variation that leads to. It leads to a bigger variation as opposed to the addition. So if you have the plus minus 1 here and you're adding 74 or 76 to 75, you're coming up with about 150 plus or minus, 1 or 2 in that final placeholder. Whereas if you do the multiplication, that'd be 5625 would be the answer if we plug it into a calculator. But our variability is going to be about plus or minus 75. Our variability is coming in a higher quantity placeholder. It's coming in that hundredths placeholder. So we're going to round this to 2 significant figures, to 5600, according to the number of sig figs in the quantity 75. Each of them has 2 sig figs, so round to 2 sig figs, whereas if we add them, we end up actually with 3 total significant figures. Okay, so moving on to number 5, 3 students determine the mass of an aspirin tablet. The results are shown below. The true mass of the tablet is known to be 0.370 grams. Which student has done the most accurate determination? So the key word here is accurate, and this is really differentiating it from precision. So precise is closeness to the target. So precision is repeatability. Accuracy is how close to the true value. So we're looking for the student who determined the average value to be the closest to 0.370. So what we would want to do here is calculate some averages or maybe compare our averages. So we're looking at A, B, and C. We're coming up well below 0.370 grams because none of the measurements actually come above the target. If we look at A, B, C, oh, sorry, I'm actually doing this the wrong way. Good lesson here in double checking our work. Student A's determinations are all here. Student B's determinations are all here, and student C's are all here. And so what we want to do is average these 3, not across the columns. We want to average the rows. So we want to average these here. These are coming out to be less than 0.370 pretty clearly. They're all well below. The next group here, we get 1 above, 2 pretty well below, and here we are almost dead on each time. So we get a little bit of variability. One of them comes lower. So it seems like student C is doing by far the most accurate work. You could you would want to look at the deviation of the values to figure out which student had the greatest variability. So like the greatest or the best precision of the measurements that come the closest together. So the worst precision would be student B. So this is the worst precision. And then we'd have to look a bit more precisely to determine which one is the most precise. Actually, they seem to have the same variability. We have some value plus or minus 0.02 higher and lower, same thing here. So it seems like student A and C have about the same precision if we're kind of considering this question asking about preciseness instead of accuracy. Okay, so moving on to number 6, the volume of a sample of magnesium weighing 5.68 grams is 3.36 milliliters. The densities of chloroform, carbon tetrachloride, and dibromomethane are 1.48, 1.59, and 2.50 grams per milliliter. On which of the liquids will the magnesium float? Okay, so we might want to calculate our density here, 5.68 grams divided by 3.36 milliliters. So we work that out. 5.68 divided by 3.36. That comes out to 1.69 grams per milliliter. And so it's going to float whenever this density is lower than the density of the liquid. If the so if we look at the first liquid chloroform, its density is 1.48 grams per milliliter. That has a lower density, so our object is going to sink. In that solution, it's also going to sink. In the next one, it's going to sink in the carbon tetrachloride. It's only going to float on the dibromomethane. So it's going to float only on the dibromomethane because it's the only solution in which the magnesium sample has a lower density. So the less dense, the less mass per unit volume, then it will float instead of sink. All right, so question 7 is a temperature conversion, 55 Kelvin over to Fahrenheit. The temperature equations, I added them in, so you'll see the equations. I just hadn't edited this document with those in them yet. What we want to do is go from perhaps Kelvin to degree C with the equations we have, then degree C over to degree F. Okay, so to get there, what we can do is use our equation that temperature in Kelvin is a degree C plus 273.15. And then take 55 Kelvin, temperature degree C, and then end up subtracting the 273.15 to get our temperature in degree C is equal to 55 minus 273.15, so minus 218 degree C. Then I need to use the equation to go to degree F. I have that directly. Degree F would be equal to 9/5 times the temperature in degree C plus 32 degrees. So that works out to 9 divided by 5 times my answer plus 32 minus 361. Answer E. And finally, convert 5.25 times 10 to the 4 centimeters cubed to meters cubed. Meters squared, I mean. From centimeters squared to square meters. We start with what we're given, 5.25 times 10 to the 4 square centimeters. Our conversion here, 100 centimeters per meter. But if we have 100 centimeters by 100 centimeters, that would be 1 meter by 1 meter. So 1 square meter would be equal to 100 squared centimeters squared. So I need to square this whole term. I've seen this a few times now. So I'm taking 5.25 times 10 to the 4. 5.25 E4 divided by 100, caret 2. So that's 5.25 square meters. Answer B. Whoop, not answer B. Need to be more careful. That is actually answer A. Okay, so that's the solutions. Thanks for the attention.